All right, day one of calculus, preparation for calculus. So this first chapter is just taking a lot of the really important things we learned in pre-calc and recapping those for calc. So section one is graphs and models. We're going to remember and talk about sketching graphs of an equation, finding intercepts, testing for symmetry with respect to the axes and origin, finding points of intersections, and then fitting models to data sets using your calculators. So first, the graph of an equation. Just remember that the solution point of an equation is possibly one of infinite solutions that exists in an equation. So if you have 3x plus y equals 7, the point 2 is a solution of the equation because when you substitute 2 in for x, you get and 1 in for y, you get both sides being equal. However, there's obviously other solutions that you could find using substitution. So one way that you could do that is you could make a table of values, you could graph, and you could find those other solutions if you had to find other solutions. So those first slides are just the idea of remember that solutions of an equation are any points that work for that equation. So you're looking for those x and y coordinates. First example, sketching a graph by plotting points. So if we needed to sketch the graph of y equals x squared minus 2, it would make sense that if you had to plot points and they specifically asked you to plot points, that you would make a table of your points. So if you notice here, the table is from -2 to 3. I'm color drawing a highlight in today. So let's see, the table goes from x values from -2 to 3. And when you substitute those in for the x values, you get the output of those y values. And then if you were to plot those points and then connect them, you would get the parabola. And hopefully you would realize at this point in your careers that this equation right here, y equals x squared minus 2, since x squared is positive, it's a parabola that opens up, and then the y-intercept is down at -2. So even before you came up with the points, you can think about what is this graph going to look like. When we talk about intercepts of a graph, two types of solution points that are especially useful are their intercepts. So their x or their y intercepts. Those are where they cross over those x-axis and the y-axis. Points called the intercepts because they're points where they intersect those axes. So if it's a point A0, it's an x-intercept. So if your y is 0, you would have an x-intercept. To find the x-intercepts of an equation, if you needed to do it algebraically, you could plug a 0 in for y and then solve the equation for x. So then opposite, to find the y-intercept, that would be when your x-coordinate is 0 and you're looking for that y value, that b value we usually use for the y. So lots of different graphs, and it's possible to have x and y-intercepts, just y-intercepts, just x-intercepts, or no intercepts at all. So obviously there's lots of different options because we're not always going to be dealing with functions. So in this example, we're going to find the x and the y-intercepts. We're going to do this algebraically. So just kind of that reminder of how we would do it algebraically. Usually the y-intercepts are going to be the easiest to find. So if we start with the y-intercept, right, your y-intercept is going to be when your x is 0. So if we plug a 0 in for x into this equation, we would just get y equals 0 cubed minus 4 times 0. So we would get that our y-intercept is 0. And if x is 0, then we know that we have the origin as one of our intersection points. And so that should clue you into then, okay, well, that's going to also be one of my x-intercepts. So if we're looking for our x-intercept, we would be looking for when y is 0. If we plug a 0 in for y, we get x cubed minus 4x. And so here what you're going to have to do is factor, right? We have it set equal to 0. We have a GCF of an x, so then we have an x squared minus 4. We know that x squared minus 4 factors into x plus 2 and x minus 2. And so if we were to set each factor equal to 0, we would get our zeros at 0, -2, and +2. So your x-intercepts will be at the origin, at -2, 0, and at 2, 0. And you should be able to do that without your calculators. All right, the next topic is the symmetry of a graph. And we touched on this last year, but we get into more of it this year. But knowing the symmetry of a graph before attempting to sketch it can be useful because then really you can potentially just reflect or rotate points. So if you have y-axis symmetry, like in this first graph, that means your y values are going to be the same, but those x values reflect, so they become opposite. If you have x-axis symmetry, your x values stay the same, but your y values reflect, and so they would become opposite. And if you have symmetry around the origin, which would mean if you were to revolve at 180 degrees, your x values and your y values both become opposite. And so you might be thinking like, well, I don't know how to determine if there's symmetry. So there's a few little tricks in determining symmetry. This is what we just talked about on that last slide. So here's your tests for symmetry. If you had to test for symmetry, the graph of an equation in x and y is symmetric to the y-axis when you replace your x values with a negative x value. So remember, when we're symmetric across that y-axis, if we're going from here to here, if we replace this positive x with this negative x, we should get the same y value either time. And if you do, you have symmetry over the y-axis. If you're testing for symmetry over the x-axis, you would replace a y with a negative y and see if you still get the same x values. And then for the origin, you're replacing the x and the y both with their opposites, with the negative x and y, simplifying and see if you still get that same equation. So when we look at that, we know we can look at the equation and find out a few things without even doing a test. Now, the question may still ask you to show, and that's where you would do the test. But here it says, it gives you a few hints. The first one is the graph of a polynomial. It has symmetry with respect to the y-axis. So again, symmetry with respect to the y means it's reflecting over the y-axis when each term has an even exponent or is a constant. So every term in your polynomial has to have an even exponent. And remember, a polynomial is in that form of y equals ax to some power plus bx to some power plus cx to some power, right? And you keep going. Your y is always raised to the first power. So the example for this would be if we have y equals 2x to the fourth minus x squared plus 2. If you notice, every term has either an even exponent or is a constant. And if that's the case, then we know that this graph is going to reflect across the y-axis. So then we can also, similarly, the graph of a polynomial has symmetry with the origin when every term has an odd exponent. So that's our example 3. So here it says, test the graph for symmetry with respect to the y-axis and the origin. So looking at this equation, because every term has an odd exponent, we know that it's going to have symmetry about the origin. But if they tell us that we're going to do the test, we're going to go through these tests just as a practice. So if we're testing the y-axis, so remember, when we test the y-axis symmetry, we replace x with negative x and see if we still get that same thing. So if we did that, we would have y equals 2 times negative x cubed minus a negative x. Or we would get y equals negative 2x cubed plus x, which is not the same as the equation. So then we would know that it doesn't have symmetry across the y-axis. If we're testing the origin, then that means that we're replacing the x with a negative x and the y with a negative y. So So if we do that, we get negative y equals 2 times negative x cubed minus a negative x. Or negative y equals negative 2x cubed plus x. And then when we divide by negative, we get y equals 2x cubed minus x, which is that original equation. And so then that would be our test to show that it does have symmetry about the origin. So the next one, finding points of intersection. Again, we're going to try to do as much as we can without the calculators. A lot of this class is going to be spent with no calculators. 2/3 of the AP test is no calculator, so we need to get used to not depending on the calculator if at all possible. So here we need to find all points of intersection between these two graphs. So what we're going to do is I would recommend rewriting the equations and making them each equal to y. Because if we know that x squared minus 3 equals y and x minus 1 equals y, then if they both equal the same thing, then we should be able to set them equal to each other. So once you set those equations equal to each other, we get x squared minus x minus 2 equals 0, right? Move everything to one side, set it equal to 0, and now you have a quadratic that we could factor into x minus 2 times x plus 1 equals 0. So our intersections are going to happen when x is 2 and when x is negative 1. And then what we need to do is actually solve for what that y value is. So what I would do then is go back up to this equation or the other one and substitute in the 2 and the negative 1 for your x. So we would have 2 minus 1 equals y. And so y would equal 1. So when x is 2, y is 1. That would be one intersection point. And if we were to plug a negative 1 in, negative 1 minus 1 equals y. So you get y is negative 2. So then the point negative 1, negative 2 would be the other intersection point. And then the last thing is fitting the linear model to data. So this is using your calculators to represent the data using a linear model. So just some reminders of what you need to do. In order to input points, you need to go to Stat, Edit, right? And you put your X into your list 1 and your Y into your list 2. So you're going to put all of those points into your list 1 and your list 2. Then you'll go back into Stat, but this time you'll go over to Calc, and you'll choose number 4, which is your linear regression, which is your AX plus B, and hit enter. And then with that, you should end up with the equation y equals 1.006x minus 0.23, right? And that would be that linear regression line.